Okay, let's look at this example for 5.1, which we are going to set up control runs for microbe-mediated reaction. The system is still a closed system with a bottle, which means we don't have flow comes in, flow come out, really focus on the reaction itself. And you imagine there's a bottle 200 milliliter in volume. We have soil, which contains some organic carbon. We also have nitrate and oxygen in the system. And we also have this magic powder and etc., which we're very excited about. So everything is ready to do this. Now, these two reactions that I put here, aerobic oxidation, denitrification reaction, these two reactions is already written as an outcome of the half reactions that we discussed earlier with the specified energy partition coefficient in terms how much goes into catabolic pathways, how much goes into anabolic pathways. Okay, so here we are looking at these two reactions, imagining that these are happening. Aerobic oxidation should occur first before denitrification. I also put the rate kinetic parameters here. So we have mu max, Km, which are half saturation constants, and inhibition coefficient, which is Ki for denitrification reaction because it's going to be inhibited by the presence of oxygen. Okay, and then we are charged to answer the question which reaction would occur first, which I already told you. But we are going to look at with the magic powder, of course. We're going to look at the evolution of the concentrations for different species. How does acetate concentration, which is organic carbon, evolve over time? In addition, we are looking at oxygen, nitrate, total inorganic carbon, biomass, etc. So let's look at our folder. Now here, when you look at this, there are several reactions. One is, there are several files. The same one is the input file. There's one database file, which is old rifle database. That one is the regular database that you have seen before, similar to like the datacom.dbs, which has a lot of reaction equilibrium constants, reaction stoichiometry as stoichiometry and primary species, second species, and all that. That's the same. One major thing that is different is now here you have two more database file, which is aqueous microbe and solid microbe. Aqueous microbe lists all the microbe-mediated reaction stoichiometry that occur in aqueous phase. For example, for this example 5.1, you have aerobic oxidation, you have nitrate, you have denitrification. All these reactions happen in the aqueous phase. So this file is for aqueous phase microbe-mediated reactions. There is another file which is solid microbe, which has the catabolic pathways for reactions that occur that involving solid phase. So for example, if you have reduction of iron oxides, these reactions stoichiometry will appear in this file instead of the previous aqueous microbial reaction file. So in this particular example, we actually don't use this solid microbe. This is putting here just for those of you who will be running solid microbe-mediated reaction involving solid phase. It's going to be handy for you later when you need this reaction stoichiometry. So what's in this aqueous solid, aqueous microbe? The reaction stoichiometry is actually not written in this complicated form you just see in the example file. So it's actually written as these two half reactions. One is catabolic. So what catabolic mean is breaking down things. So essentially it's the oxidation of acetate here becoming inorganic carbon, which is bicarbonate. So you have essentially you have these reactions that happen, right? This you think about this KQ value. This should be capital K. This KQ value is more like a dummy number. It's big, so which means it's not going to functioning as limiting the reactions. The reaction almost always for these redox reactions reaction almost occur always in the direction from left to right, meaning as acetate become bicarbonate, as long as you have the reactants that are still there. So that's catabolic, but you also notice there's another anabolic reaction, which includes, for example, the buildup of bacteria. So you have C5H7O2. Anabolic means building up things. So essentially, this reaction is indicating using the ammonium and acetate to build up microbial material C5H7O2, and which is using the bacteria is using oxygen. So this is how you figure out, okay, this bacteria is for the oxygen reducing bacteria or microorganism. So you have these two, and in the online material we talk about how much the energy produced from the reduction of oxygen would goes to the catabolic pathway and anabolic pathway, and this is Fs and Fe values are essentially for these purposes. So if you look at back in this, so here we're saying Fs and Fe is the number for aerobic, and it's different for denitrification, which is determined by reaction thermodynamics. Okay, so you will be looking at this, and so what's in the input file? Let me open the input file. In the input file, so as I mentioned, the key difference is you have these two additional databases. Essentially, in this case, it will be really one additional database. So everything else will be very similar. You have the runtime, you're reading database, you have output keyword blocks, putting in these different time series, and you also have these, for example, discretization, which you only have one grid block. You should have the total volume of 200 milliliter, which is here is 200 centimeter cube, which is same as 200 milliliter. You don't have boundary condition because it's closed system. You have initial conditions. So let's look at aqueous kinetics. So if you think about the aqueous kinetics, right, you have the anaerobic oxidation. And you're essentially picking up the name. You need to, this block is different in the sense, okay, you will need to specify aerobic oxidation reaction, the pathway you have for aerobic oxidation half. So this name is there to be the same as this name, which is the catabolic pathway. So once it recognizes this, it will read in this reaction stoichiometry. And then you will be also in the input file, you have another pathway which is with this name, which the code will be picking up this pathway, picking up this name and process. Okay, so here you have aqueous kinetics block, and this aerobic oxidation H5 is defined as for the aerobic oxidation reaction. We actually don't need this HW5 if this is really not necessary. You can just actually, all the code is looking for is this name and the other name here. So this is for the catabolic pathways. This is for the anabolic pathways that build up the C5H7O2N, which is oxygen reducing microbe. So if you go back into, for example, the aqueous microbe, the corresponding name is here, so it will take up for catabolic. You will have this reaction stoichiometry put in, it will be using by the code. And when it sees this, it will have this set of reaction stoichiometry reading. Now we also talk about those Fs and Fe values, right? So in the input file, you are actually putting the 0.4, the Fs and Fe value here and here. So this is essentially the Fe values, 0.4. And 0.4 and 0.6. So these are how you specify these Fs, Fe values. Otherwise, so essentially the code is already programmed to read in these half fractions and then use these Fs and Fd values to come up with overall reaction as we indicated here. So you don't need to worry about changes, like do this detailed calculation. As long as you have the Fs and Fe values, you're able to construct that. And then this rate is a mu max. So actually in this aqueous microbe, you also have, so the top part is the reaction stoichiometry, and then the bottom part is there's aqueous kinetics in the bottom part. And so the bottom part essentially is telling you the reaction of the form, okay, rate expressions, the form of the rate law. Oh, actually, so this term needs, if you have H5 here, HW5, that's what I'm talking about. This name need to be the same name as what you have here. So if the database, it says have this dash or underscore H homework 5, then you do need it here. They need to be consistent as a kinetic block. Anyway, so look at this. We talk about all the reaction for monod kinetics. So this rate is essentially mu max. It's the same as input file. And then you have monod term, which means it depends on total acetate, aqueous oxygen concentration. These values are the Km value for acetate. This is the Km value for oxygen, which is the same as what you have here. So all these parameters essentially in the later part of the bottom part of the input in the database aqueous microbe. Same for denitrification reaction, which I'm not going to detail. So here, and essentially what you have here is, okay, aerobic oxidation H5. The code will be looking for both reaction stoichiometry of the two half reaction, build up the reaction, and then do the look for also kinetic information. Same for nitrate reduction inhibition homework 5. So you just corresponding blocks for this reaction and also for catabolic and anabolic. Notice that here your Fs and Fe numbers are different now, right? This would be the Fe actually. This is Fs. So they're different, and because of the reaction dynamics for microwave mediated reactions. So these are the aqueous kinetics. And pay attention that with all these reactions, when you look at the reaction in the database, it's important that you put these, for example, primary species acetate, ammonium, nitrate, oxygen in the primary species, bicarbonate, for example. The other things that are really important is that if you think about how we represent the biomass, right? So biomass, a lot of time once they are coming out of the consumption of organic carbon, they can either stay in the water phase or a lot of times they attach to a solid phase and form biofilm, and it's not as mobile as in the water phase. So a lot of time and actually a lot of literature has been showing that biomass this is a big tendency forming biomass or biofilms. They are not very mobile. So essentially what we do in the code, if you look at these reaction stoichiometric, they are really producing aqueous microbe, right? These are aqueous phases. But then we are saying once they are produced, they will quickly become solid phase attached on the surface. So we're actually using a kind of a precipitation reaction to approximate that process. So there's a reaction related to this, and there's a solid phase called a mineral. Yeah, so the solid phase species. So you have this C5H7O2N O2, C5H5O2N NO2 NO3, right? So these are O2 NO3. These are the species that actually goes into representing the biofilm. So we put a relatively small kind of, they still follow TST radar as an approximation, but we put you can put small KEQ or larger KEQ values to control how much the biomass can be in the aqueous phase. The majority of them usually come into the solid phase quickly or biofilm phase quickly, and use these reaction rates to represent how fast they become biofilm. If you put these very small values, like for example 10 to minus 8, 10 to minus 10, then a lot of biomass will be flushing out because the resin time is fast. The resin time is short compared to the precipitation reaction to happen. So you want to put these rates relatively high if you want to see a lot of biomass actually goes through solid phase. And quasi is representing, put it here to say, okay, there are essentially soil, like soil is a majority, a lot of them are quartz. That's why it's here. But it's not actually not necessary to be here because it's not involving any other reactions. Let me see. So primary species, secondary species, these are all necessary reaction. And then you have these conditions, right? So the initial condition, You want to be consistent with the example. There are the different chemical species. We put this very, the example really, the condition doesn't give you this. We usually put this for small numbers. Bacteria will build up quickly. And let me see. So these condition and then other, so you do need to put a solid phase to represent the biomass, and we do put some volume fraction here to represent initial amount of these biomass here. A lot of time these concept these they're like volume fraction essentially. If you put very small numbers, the system will need to take a long time to build up enough biomass. So you'll see concentration decrease at some point. So that if you put small numbers, there will be a lag phase in terms of how much biomass need to grow first before they actually functioning to allow you to see changes in concentrations. So this is for the input file. For the solid microbe, actually the setup in the system that you only have reaction stoichiometric there. The reaction kinetics are actually still in the old rifle database because these reaction originally was already there. The aqueous microbe was added later on, so it's a bit different there. But anyway, in one of these or two of these files, you will find the reaction stoichiometry and reaction kinetics. So let's run this. So everything is put in there. Let's run this, and we can kind of quickly walk through the output file. So if we look at the output file, each of these have 4 times 1, 2, 3, 4, and that's because in this file we have put in the spatial profile we have 1, 10, 20, 30, 4 times points. It really for the batch reactor, it's these spatial profile are not necessary. You can comment them out. If you would like to do that, then we can actually, let me just do this so it's your output file is a bit cleaner. You really don't need that much file. So I'm deleting all this, and I'm going to change, like just comment out, so then it wouldn't have spatial profile coming out. And let's rerun it. Oh, okay, sorry. So I do need that, but I can just put, because I do need this spatial profile to give the time points when it's going to end. So let's put 30, which means it's going to be end in a month. So you do need this. This is necessary for a way to look at the time evolution. You can just put 1, so you would only have 1 spatial profile coming out. So let's rerun it. Okay, now you have all this, and you notice every one of these species only have 1, right? So it's like, because I only give 1 time point for the code to spit out the spatial profile. But what we are really looking at should be time series, which is essentially it's kind of later on when we introduce column exponent, it's kind of like breakthrough curves. So this will give you, and the gray box is the gray box number. We have 1 gray number. This will give the time evolution of these chemical species in this particular gray box. So let's look at this file. So this will be the file that we rely on to plot out the concentration of different species. See, okay, it's here. Okay, so you can look at, okay, time, pH, oxygen, NO3, N2, acetate, bicarbonate. And this is a bit harder to see, but it's the easiest way would be you export them either in Excel or read them in MATLAB and then directly plot. And actually, so let me just close this. The output for this example is really this. So we have already plotted out. You can see this. The reaction 1, of course, would occur first. And you can look at the concentration as a function of time until 30 days, right? So what does this tell you is this is based on that biochemical output, right? So oxygen, we talk about oxygen will be consumed first. So O2 is coming down and not coming back again because it's being consumed. And then at first, nitrate still remain like it's flat, meaning it's not much reduced. But then it's reduced. It wasn't reduced right after oxygen is consumed. The reason why, if you look at the input file, you realize that nitrate have a relatively small concentration at the beginning. So that's what I'm talking about. First of all, it has a lower rates than aerobic. For example, mu max is much smaller, and also initially it doesn't have as much biomass there. So essentially, nitrate, the denitrification biomass need to build up for some time. So that's why you see very flat, even after oxygen is consumed, remain flat for a certain period of time, about 10 days, and then start to get down because at that time there's enough bacteria build up. And it's actually, you can see that in this bacteria biomass figure, right? Biomass as a function of time. And you have the nitrate reducing bacteria build up. Early on, it's relatively small. It takes some time to build up, right? Take a bit of time to build up. And then the oxygen reducing bacteria increase quickly because it has rates, faster rates. And once they get to the point about beyond 5, it remain constant because it does not grow anymore. Oxygen is all gone. Now, correspondingly, you see for acetate, so both reaction consume acetate, and they are producing DIC, which is bicarbonate, right? So acetate is being reduced. Why you see this kind of changing almost like in slope here? Because oxygen reduction is much faster, just as this is same slope here. And then this one is almost mirror the nitrate concentration. So essentially, this is corresponding to the consumption of acetate by nitrate. And these two essentially mirror each other with this almost symmetric reaction stoichiometry, right? So DIC increase quickly first, but then slow down until denitrification reach certain rates that are higher. So these are things that you can actually look at and think about. So in this one, you do see the redox ladder. Oxygen occur first, nitrate occur second, but it doesn't occur right away after oxygen because it has a bit of lag time. So this is example 5.1, and homework have some extension questions that are related, but there's also another reaction that I asked you to look at, which is sulfate. So you will be looking at the different files and the sulfate related reactions.